All right, folks. Well, welcome back. I was kind of a little bit crazy yesterday with connectivity issues, and then trying to get things worked out here. So hopefully everyone was able to get on, watch the video, and finish the assignment. If you did not get it done, please let me know. Please email me or comment on our classroom page, and then that way, then I can make sure that I give you more time to work on the assignment. Okay. But like I said, hopefully that those issues were taken care of, and we'll be able to move on. Okay. All right. So at the end of the video yesterday, we were drawing Lewis dot structures for different compounds. We saw then that most atoms make sure that with most atoms you are able to complete their electron configuration so that they have the electron configuration of either helium or one of the other noble gases. But we did see then that there were exceptions to that rule, where we had some atoms that did not have the complete octet, that they were deficient in their octet, or we had atoms that expanded their octet, which means that they had more electrons than the 8 that usually would make up a noble gas. And so there are those exceptions there, and so make sure you keep that in mind, that typically these exceptions will either be boron or beryllium for the atoms that are deficient, and then atoms that are in the larger atoms, group three, row three atoms, they will tend to be expanding their octet in order to complete the structure. Okay, so make sure you keep in mind though that there are certain atoms that will always need to make sure that their octet is maintained. Carbon, nitrogen, all the halogens, oxygen. And so for the most part, you can follow that rule, and that should help you figure out which atoms can and cannot violate the octet rule. And then finally with helium, the helium must always have there too. Okay, so with that said then, hopefully, come on by after school today, get your questions answered if you have any questions on it. Okay. All right. But there are certain molecules then that when you draw them, there's going to be more than one valid structure that you can make, and valid structure then meaning then that all the atoms will meet up with their octet, or all the atoms will fit into the octet rule. Okay. And yet still there will be different structures. An example here there would be the nitrate ion. So if we take a look at the nitrate ion, let's go ahead and take a look at the structures for nitrate. You know, get this, there are three equivalent structures, and they are not the same. They're not the same. So if you take a look at the very first structure here, the double bond sits between nitrogen and the oxygen on the bottom. In the middle structure here, the double bond now is shifted over to the nitrogen and the oxygen on the left-hand side. And then finally, with the last structure on the right here, the double bond sits between the nitrogen and the oxygen on the right-hand side. So it looks like here the double bonds have been drawn in different locations for each one of these structures. So they are not the same structure. They are all valid structures. Every atom has their 8 electrons, okay, and we've accounted for these 24 electrons in each one of these structures. Okay. All right, so what we've done here is that we've drawn equivalent structures. These are equivalent, meaning then that they are equal and equally valid. Okay, however, they are not the same. Okay, so this is what we refer to in chemistry as resonance, and this is one of the another one of the problems with the localized electron model. So this localized electron model, remember, so when we talk about localized electron model, what we are referring to is the electrons being localized between the atoms that share those electrons. So for example, in a single bond, the two electrons that are shared between two atoms, in the localized electron model, those electrons, they stay put. They stay between those two electrons. Okay? And so this gives rise to, this is where the localized, this gives rise to one of the main issues, the main problems with the localized electron model, and that is it really doesn't fit in with quantum mechanical data. And that is, remember with quantum mechanical, according to the quantum mechanical theory, we can't say where the electrons are. We don't know where they are. And so one of the ways that the localized electron model tries to account for the delocalization, so this represents the delocalization of electrons, is by saying then that we have this phenomenon known as resonance. Resonance meaning then that the electrons are able to move around. So what happens here, and you learn this much more later on, is that actually electrons are able to shift around, they move around, and as they move around, they alternate. These bonds look like as if they alternate. Okay? And so resonance, it helps to explain then the delocalization of electrons within a molecule. Okay, we know that electrons are delocalized in an atom. They can move from one orbital to another. We saw that happening back in chapter 7. Okay, and so here then, the idea behind resonance is that you take the localized electron model, you take this particular model here, and you try to explain then the delocalization of electrons within a molecule and not an atom. Okay? And so we have here our equivalent structures, meaning that they are all the same. They are not different. They are equally valid. Each one of these structures is equally valid. And so we essentially have then, when we draw these structures, we typically draw them as if they were a single molecule. Okay, so we draw a structure that represents somewhat the average of all of those three. So we can all draw all three, but that takes a lot of work. And so what we do then is that in order to represent this delocalization, okay, we can draw what's called an equivalent structure. And this equivalent structure roughly represents a chimeric structure. A chimeric structure meaning then a structure that's made up of the other structures. And so if you follow mythology at all, a chimera is a mythical monster that's made up of four total creatures. Okay? All right, so basically what we do then is this resonance structure can be drawn in a similar manner. So if we were to draw the structure for nitrate, if we draw the structure for nitrate, okay, what we would do then is we would draw the nitrogen. Okay, we would indicate then the oxygens that are located around the nitrogen. Okay, and then in terms of the bond then, and this is actually what we do see with the bonds between nitrogen and oxygen. I'm going to leave the lone pairs out just for now. Okay, now we see then that the oxygen and the nitrogen, the bonds between them is not full single bond or full double bond. It's actually a bond that sits in between. You can think of it as a bond that's about 1.5, and it's not actually 1.5, but the bond characteristics here, that is the bond energy and the bond length here, sits somewhere between that of a single bond and a double bond. It's not quite all single, it's not quite all double like we had represented in the previous slide, okay? But the actual bond length and the bond energy here is somewhere between a single bond and a double bond, okay? So the bond characteristics of this nitrate atom shows then that the bond here itself is not a full single bond and it's not a full double bond either, okay? So it's somewhere in between, and so this is how then we represent the delocalization of these atoms, of these bonds. Okay. All right. So with that said, then that's one issue that you'll have to deal with when we deal with Lewis dot structures. Okay. All right. Let's go ahead and let's practice a little bit more. What I'd like us to do then. Let's go ahead and let's draw a few of these structures here. Let's start out with carbon monoxide. Okay. So with carbon monoxide, let's make sure you keep in mind then that you want to make sure then that when you draw these, the center atom is always going to be carbon, like I pointed out to you. Okay, so carbon monoxide, then if we draw this, carbon's going to have a 4 electrons. And so initially, if you need to, draw these out, okay, and help you with this. Okay, so I'm going to draw these structures here. Okay, and so if you draw a double bond here between carbon and oxygen, okay, then you really, the oxygen has its octet, but carbon does not. Remember, carbon and oxygen both must have their octet. So here you have 2, 4, 6, 8, but you have 2, 4, 6 on carbon. Okay? And so what's going to happen here then is that the third of this triple bond, so hopefully you'll see then that a triple bond has to form here, okay, will come from these electrons here. So if you notice here with this bond and this bond, these 2 bonds here, each atom, the carbon and the oxygen, contribute an electron each. So they equally contribute to each one of these bonds here. But if only a double bond forms, carbon then does not have its octet. And so what happens then is oxygen then goes ahead and contributes a bond. Okay, so this bond here is formed from one of the lone pairs on oxygen, sharing oxygen, taking one of its lone pairs and sharing it with carbon. Okay, so this bond is a covalent bond because two electrons are being shared between carbon and oxygen. It's just this time the two electrons come from oxygen. And so remember, we talked about this type of bond back in first year chemistry as a coordinate covalent bond. And so these coordinate covalent bonds are not, and keep this in mind, they're not actual bonds themselves, and they're not, so it's not a fourth type of covalent bond. Okay? It's just the way that we account for why carbon and oxygen, when they get together to form carbon monoxide, that they actually form a triple bond, and that each of these atoms will have a lone pair left over at the end. Okay? And the only way you can account for that is by saying then that one of the bonds of the triple bond here is a coordinate covalent bond that comes from oxygen by itself. Okay, so with that said then, the structure for carbon monoxide then is a triple bond. And so the bond energy, so the measures of bond energy and bond length confirms then that this is a triple bond right here. And again, the only way that we can account for how carbon and oxygen can share this triple bond in our Lewis dot structure is by indicating then that we have this coordinate covalent bond that comes from oxygen. Okay. All right, very good. So please make sure you practice this. Okay, so let me go ahead and clear that out. Okay, and let's go ahead and let's take a look at another structure, and let's draw that one together. Okay, let's take a look at carbon dioxide. Okay, so let's go ahead and take a look at that one really quickly. Okay, and so same thing here. If we draw carbon dioxide, let's go ahead and do this here. Oh, so I'm sorry. There, I forgot. There was 10 electrons that we had to account for here. 10 valence electrons we have to account for here, and so the structure we drew accounts for that. All right, so for carbon dioxide, then we have to count for 16 electrons in our structure, 16 valence electrons in our structure. Again, carbon's going to be the center atom. Okay, double bond forming between carbon and each oxygen. Okay, and each oxygen then will hold on to their lone pairs, and no coordinate covalent bonds here. If you draw these out here, the carbon just forms each atom contributes 2 electrons in each one of these double bonds. Okay? So there is your structure for carbon dioxide, 16 electrons counted for in this structure here. Okay. All right, let's go ahead and let's take a look at another one. Let's take a look at another one here. Let's go ahead. Okay, let's look at this structure here. Okay, so let's draw this one and make sure you understand that when we draw this, carbon's going to be the center atom. So carbon's going to be the center atom. Let's go ahead and do that. Okay, and so and I'm going to draw the dots again. And I'm sorry, with methanol here, so this is methanol, we have to account for 14 total electrons. Okay, 14 total electrons. Okay, and let's connect the dots in really quick to see how this works. Okay? So we have to have 3 oxygens, 3 hydrogens, oxygen, and another hydrogen here to surround it. Now, if you do this enough, and it takes practice, folks. So make sure you keep practicing with step D for your homework tonight. And if you draw this here, you notice if we put the 4 hydrogens around here, we're done. Carbon cannot form any more bonds. Carbon can only form a maximum of 4 bonds, whether that's 4 single bonds, 2 double bonds, or a triple bond and a single bond. Carbon can only form a maximum of 4 bonds. Okay? And so if the hydrogens gather around here, then that means that oxygen cannot be a part of this molecule. So therefore, this carbon then has to be attached to 3 of those hydrogens, okay, and 1 oxygen. So you can have 3 single bonds, 3 carbon hydrogen single bonds, and then this oxygen will come in. Okay, and I'm going to draw it this way here. Okay, and it will form a single bond with carbon as well. And then the last hydrogen then will form with oxygen. And there we've now accounted for all 14 of these valence electrons. If you count, we have 1, 2, 3, 4, 5, 6, 7. There are 14. And so the structure of methanol then will be 3 single bonds that hydrogen forms with carbon. So you have 3 carbon hydrogen single bonds, 1 carbon oxygen single bond, and 1 oxygen, hydrogen, single bond with 2 lone pairs left on oxygen. Okay? So that's how you'll go about drawing the structure for methanol. So that's like I said, initially it's going to be trial and error, folks. You got to just draw out these dots, plug them in, and try it. Okay, but it's at a certain point as you get better at this, you're going to be able to see how these pictures, how you draw out these structures and where they should go. Okay, let's take a look at one last one here. Okay, so we have the cyanate ion. Let's go ahead and draw this one here. Okay. So with the cyanate ion, again, carbon's going to be the center atom. Here, this represents this negative sign here. It means that we're going to add in an extra electron at the end of this process. Okay, so with the cyanate ion, then we have to account for 16 total electrons. Okay, 16 total valence electrons. Okay. Okay. So you got 6, 4, 5, and then one more would be 16. Carbon's going to be your center atom here. Let's start out with, and I'm going to draw this here. So we have a carbon, nitrogen, triple bond, okay, here. Okay, and then we have oxygen, carbon, oxygen, single bond, okay, with the 2 valence electrons here. Okay, and then the extra electron coming in, right there, form that. Okay, so let's make sure with this particular structure, we account for all 16 electrons here. You have 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8. There are 16. So this is a valid structure right here. This is a structure that we can draw for the cyanate ion, which is going to be negative on the side because you've added an extra electron. However, let's go ahead and I want to share this with you. Let's go ahead and see if this is a valid structure here. Where we form a double bond, the carbon forming a double bond with oxygen and nitrogen. And again, the extra electron coming in with the oxygen here. Would this be a valid structure? Well, let's go ahead and again count all the electrons here and see if we have accounted for all 16. So 1, 2, 3, 4, 5, 6, 7, 8. This also is a valid structure because every atom has their octet. So 2, 4, 6, 8 for nitrogen, 2, 4, 6, 8 for oxygen, 2, 4, 6, 8 for carbon. Okay? And same thing holds true for this structure here. So this is also a valid structure for cyanate. And then finally, what about this one here? Well, we have a triple bond on carbon and oxygen. Okay. And we have a single bond with nitrogen and the extra electron coming in on nitrogen. So with this particular structure here, so we have them 1, 2, 3, 4, 5, 6, 7, 8. And we also have 16 electrons here. All of the atoms have their 8. Okay? And so this is also a valid structure. So here then is an example, another example of resonance that occurs in drawing the Lewis dot structure. Okay. All right. What I'd like you to do then, let's go ahead. Let's continue on with this then, and take a look at number 10 in your problem set. And I'm going to ask you to. I'm going to ask you to go ahead then and draw the structure for the nitrite ion. So take a couple minutes, draw the structure for the nitrite ion, and let's see what you come up with. And when you get back, we'll compare answers. Okay, so go ahead, draw out the structure for the nitrite ion. Okay, let's go ahead and let's take a look at the nitrite ion then, and let's draw it out. So here, nitrogen is going to be the center atom. Okay, nitrogen will be your center atom, and I'm sorry, nitrite then, we have to account for 18 total electrons. Okay, because you have 12 and 5 would be 17, but you get the extra electron that comes in. Right, so let's go ahead and draw this here. And again, if you aren't quite sure how we get this, please make sure you come by after school today and get that extra out. But a double bond between one oxygen and the nitrogen. Okay, and you have the 2 lone pairs here, lone pair on nitrogen. Okay, and then oxygen here, then single bond with the extra electron coming in on this oxygen here. And so this is a structure, one possible structure for nitrite. Let's account then for the 18 valence electrons. You have 1, 2, 3, 4, 5, 6, 7, 8, 9. And so there is a structure for nitrite. Okay. Now, let's imagine then if the double bond shifted. Okay, and so let's say then the double bond now falls to the electron oxygen on the right-hand side. Okay, is that a valid structure for nitrite? And the answer obviously is yes. And so we see here another example of resonance here as well. And essentially what's happening here, and you'll pick up on this more as you go into, for example, organic chemistry. What's happening here then is that the electrons actually shift around. So you have that electron coming in there, okay? And what'll happen then is, as a result then, I'm sorry, yeah, and so as a result then, um, this electron will shift out that way, okay, in order for all the atoms to maintain their octet. So we have the movement of electrons that occur in this particular molecule right here, okay? All right, one last thing I want to ask you to do real quick before we finish up here, and what happens then if the structure, and I want you to draw, so this is nitrite, what would the structure for nitrogen dioxide be, which is the neutral, this is a neutral molecule here. So this molecule does exist. Okay? So here we had 18 valence electrons, remember. Here we're going to have 17 valence electrons. Okay? And so what would this structure look like here? So let's draw this out and see what happens. Okay? All right, so here we have an odd number of electrons. And with an odd number of electrons, folks, there's no way that, that we will achieve the octet for all three of these atoms. And so in these cases here, what we're going to notice happening, and I'll draw the structure out for you, what we're going to notice happening here, and let's draw out this structure here, and let's connect the dots. Okay, okay. So we have one oxygen here, and I'm going to draw another oxygen here, and hopefully you'll see why in just a moment. Okay. All right. So we're going to form a double bond here between the oxygen and this oxygen on the left and nitrogen. That'll complete the octet for this particular oxygen here. Okay. All right. And so if you take a look at this here, this oxygen then, if it forms a bond on this side here, neither the nitrogen nor the oxygen will have its octet. And so this is an odd thing that happens here. So what will happen, and I'll draw this for you. Okay, what will happen then is that there will be a coordinate covalent bond that forms between this oxygen and this nitrogen, with this lone pair here going to form that bond. Oxygen, this oxygen on the top here does not contribute any. So the single bond that forms between the oxygen on the top here and the nitrogen, those two electrons come only directly from the nitrogen. Okay? And so that with that said, then this oxygen will obtain its octet. And so here lies then the last exception to the octet rule that we have to keep in mind. And that is whenever there is an odd number of electrons, you will not get, one of those atoms will not achieve their octet. And typically we see this happening with nitrogen, but with phosphorus as well. But again, we saw with phosphorus and the higher atoms, they can achieve, they'll violate their octet more often by expanding their octet. Okay, so with that said, then when you have an odd number molecule with an odd number of electrons, that extra electron will fall with the nitrogen. So when you draw these structures out, if you're asked to do that on the AP exam, just make sure you keep that in mind. Okay. All right. Well, that ends my time here, folks. And so what I'll do is that's it for Lewis dot structures, folks. Tomorrow, then we're going to continue on with formal charges. So please make sure you take a look at that section. I'll explain what those are. I'll assign one last problem here for you to help you practice with Lewis dot structures, but please make sure you practice these. Make sure you account for the exceptions to the octet rule. And so make sure you work through these and practice them. The more you practice them, the more you'll be able to kind of see pretty straightforward what has to happen, okay? How these structures come together. Okay, all right, so good job. Hopefully come by and see me after school today, folks, 3:15 to 4:15 if you want to practice drawing these Lewis dot structures, but I think these end up being pretty straightforward. Okay, so please make sure you get the last problem done from the book, and then I will see you folks tomorrow or this afternoon. Okay.